Hey, I just wanted to make a video on this practice quiz since I'm not in today, so that way you can just get a verbal explanation. Okay, so I've already done the answers, so I'm just going to walk you through them. Okay, the first question, I started by doing like power over power law with the exponent of 3. So that's how I got the numerator. And then I just used the division law to simplify. Sorry, feel free to pause this video anytime. I'm going to try to go fast. The next one, I did the same. I did power over power law with the exponent. And so applied my exponent to each thing. I tried to just show how I got these in case you forget how to multiply exponents or how to multiply fractions. So like 12 times negative 12 times negative a third ends up being 4. So I showed my work over here in case you have trouble with that. And then, just a reminder that a fractional exponent, like these guys, the bottom number indicates the root, so it's the cubed root, and the top number is the exponent of 1. Okay, then this graphing one was pretty straightforward. I just did a table in my head to kind of like figure out where all the points would go, and I graphed it. Got the domain and range, the asymptote. It's an increasing function because it's going up to the right. Increasing to the right. The transformations guy, I just went point by point kind of. So I applied my reflection, my stretch, and then I shifted it. So just as an example, I want to do an example point. Let's say I took this point right here. So that is at 1, 2. So just looking at my y values, I know that, just looking at my x value first, I know that a reflection in the y-axis is going to cause that point to become right there. It's going to get reflected over the y-axis. Then if I apply my stretch of 2, I know it's sitting at y equals 2 right now. So if I double that, it's going to be at 4. And then it's going to get shifted down 1. So that becomes that purple point right there that I plotted. So like that's what happened to this point. It became that point. So that's how I just transformed all of that. Or just as an alternative, I showed that by subbing in a value that you might need, like x equals -2. I was thinking, I wonder what the value is if I don't want to transform a point. I could just sub it in to where my x is. And I found out that it would be at 7. So you got a couple options. You can perform the reflections in terms of like doing A and K first, and then moving on to if you have a C or a D, then you would apply those transformations. Or you can just like try subbing stuff in, even like to get the y-intercept or to get some points. The asymptote is always this guy. So we got the asymptote by just knowing that's a -1. And that's it. Question 2 is a little challenging, especially if you don't have a super awesome handle on transformations. So write 2 equations to represent the same exponential function. That part's tricky. So you got a y-intercept of 5 and an asymptote at 3. So I feel like the asymptote's pretty easy. Just putting in the c value of 3 gives you an asymptote at 3. So that takes care of that. Then you got some options. You could really pick any base you wanted to here. I picked 2, but you could accomplish the same goal if you picked 3 and then a third. So just knowing how functions are related to each other really helps with this question. So I picked 2, and I knew that when I'm using the y-intercept, I know that a y-intercept occurs when x is 0, so 2 to the power of 0 will end up being 1. So I knew that I needed to have a vertical stretch here of 2 because I want my y-intercept to be 5. So I knew that when I had a 0 in here for the x-intercept, this thing would become 1. 1 times 2 is 2, and 2 plus 3 would give me a y-intercept of 5. So like I needed some of these things to be here. I needed this too. And then the base didn't really matter. Like I could have picked 17 if I wanted to. It didn't really matter. And then if I want another equation that represents the exact same exponential function, one really like the easiest way to go would be to use the decreasing function that matches 2 to the x. So you should know that y equals 2 to the x and y equals a half to the x are reflections along the y of each other. So they are identical, but they're flipped along the y-axis. So that's what they look like. So by making this base a half and then applying a reflection in the y-axis, that allowed them both to look like this highlighted one. So that was like a cool thing to do. So if you would have used the base of if you would have used the base of 3, you would have had to use 1/3 in your other equation. So that one's kind of tricky, but it's a neat question that really tests whether you kind of understand the basic exponential functions, like what they look like, and some of the transformations. And even exponent laws come into play. This solving for x one just required you to make 32 into 2 to the power of 5, and then you just set the exponents equal to each other. Okay, determine what type of function the following are. We didn't spend very much time on this, if any, really. So this would just come from all prior knowledge stuff. It won't be a big component of the test. You should be able to identify a straight line as being linear. That's a grade 9 expectation, and I mean, that's not something you probably should forget. Straight lines are always linear. So that's how we know that. I'm going to move on to the third one. This, we just did a unit on quadratics. So we should know that if we have a function that's a degree 2, we know it's quadratic. That's what a quadratic function looks like. So if we have an exponent of 2 as the highest exponent, that is a quadratic function. And then moving on, this is less familiar, exponential. It turns out, well, we knew it wouldn't be linear or quadratic because the y values don't follow the pattern that linear and quadratic do. Linear would have the same first differences and quadratic would have the same second differences, which they don't have. So what exponential functions have is they have what's called a common ratio. And that means if you were to divide this number by this number, you would get a half. So this has a common ratio of a half. I said it's getting divided by 2 each time, but another way to write it would be the common ratio is a half. 4 divided by 8 is a half. 2 divided by 4 is a half. 1 divided by 2 is a half. So when you divide the bottom number by the top number, you should get the same number every time for an exponential function, and we call that a common ratio. Whereas, like, for example, quadratics, they don't have a common ratio. They have common second differences. So if this was a quadratic function, you would see, oh, it's increasing by 1, then it's increasing by 3, then it's increasing by 5. But if we look at the second differences, they're always 2. Whereas a linear, if we looked at a linear table of values, we could see that they would go up by the exact same amount every time. So they increase by 5 every time. That's what makes them a straight line. So you should be familiar with that. That's good to know. And then finally, exponential growth and decay. So this is just a radioactive isotope one. So we've got an initial mass of 8 and half-life. So we know the base would be a half. The half-life is 2.5. So that would go in the denominator of our exponent. And t, we don't know. We're trying to find possibly, or we will know in part B. So part B says find the amount remaining after 10 days, after 15 days. So we're going to sub that in for t each of those times and just calculate it using a calculator, which if you don't have one, you should get one. Seriously, calculators are handy. How long will it take for the sample to decay to 15%? This one was harder. So 15% of 8 is 1.2 milligrams. So we sub that in for that amount. And x, that's what we're trying to find. What's the time? So I decided to divide both sides by 8 just because I thought it would clean it up a little. So now my equation became this, which looks a little less, I don't know, a little less stuff in it. Now, here's where you're guessing. It's actually super annoying. You're just trying to figure out what could t be to make this equal 0.15. So I decided to say, you know, I don't care about that fraction in the exponent. I'm just going to say 0.5x equals 0.15. So I'm like, what could this be? So it equals this. And literally I just went through. I'm like, what if it's 1? No, that doesn't work. What if it's 2? No. What if it's 3? No, but it's got to be in between here because it's 0.15. So it's got to be in between 2 and 3. So then I just started at 2.5. I was like, oh, that's too big. Well, like the answer's too big. So I'll try 2.6. Still too big. 2.7. Oh, that's pretty accurate. It had a bunch of decimals after it. So I was like, that seems close enough. 1 decimal place, I think that's totally fine. So now I knew the exponent is 2.7. But that just means that 0.5 to the power of 2.7 equals 0.15. But our exponent was this crazy fraction, not just a whole number. Or that's not a whole number, but you know what I mean. Not one number. So I knew I had to set my exponent equal to 2.7 and solve for t. So I got 6.75. Not exact, but close enough. If you want exact, you'd have to use logarithms, which we don't learn until grade 12, but some people have been investigating them. So if you are, I just showed my answer using logs, and I got 6.84, which is pretty close to the one I got before. And that's it, really. That's the whole practice test. If you can do that, I think you'll be pretty good for the test. I just had this was on, I think I posted this yesterday, talked about it with a couple people. If you're struggling with growth and decay questions, this is a good way to look at it. So this is like generally what they always look like. Initial amount, that's your growth or decay rate. Sometimes this is time. And then you basically have questions are split into 3 groups. They're either talking about doubling time, like if it's a bacteria or something, when the base is 2, and D is the amount of time it takes to double. Maybe you're looking at a radioactive isotope, half-life, where the base is a half. Your exponent is a fraction because you got some kind of half-life time going on. Or it's some kind of percent thing. In which case, you got to change the percent to a decimal. And if it's growing, you're going to add 1 to that decimal, so 1.05. If it's decaying by 5%, you're going to change 5% to a decimal and then do 1 minus that decimal because you'll have 95% of your material every year or every time period. So that's how that works. So this slide here should be able to get you through any growth and decay question, I think. I hope. I think so. And then just paying attention to what they're asking for. Are they looking for the initial amount? Maybe you know this value, but you don't know this value. So just paying attention to what they're looking for. And that's it.